Okay, so my name is Katarzyna and I am, what? Okay. Without the soundtrack, it won't be the same. Okay, so I'm going to tell you some things about search, text search to be more specific. But before I do, a few words about me. I graduated from Polish philology. Then I spent like 7 years being a genealogical researcher. And about 4 years ago, I converted to programming, and I'm still in it, yeah. At the beginning of my programming path, I stumbled upon this wonderful company, and I'm staying there. Thank you, Rebased. And the current project I'm in is an e-commerce app, and my main task is the search mechanism. The first part was to replace existing search mechanism which was based on PostgreSQL with the one based on Elasticsearch. So, as I have no formal programming educational background, when I've heard the word Elasticsearch, well, my imposter syndrome got like through the roof. And then I went into Chuck Norris mode and I read the whole internet. And I learned plenty of things. That is what Elasticsearch is, this guy. Elasticsearch is like, self-sufficient, having all options you can imagine, each option you can imagine, right? And it's a huge and powerful tool, basically for allowing you to build your search. And it takes like, I don't know, million years to master it. And that's why I will not tell you about Elasticsearch today anything. But instead, I will tell you something about information retrieval solutions that are underlying Elasticsearch and probably every other search tool you can find. Before, though, I will tell you exactly what information retrieval is. Let's think about search for just a moment. Well, I think about search as about communication act. And in communication act, you've got this user, and the user has a computer, and user asks computer about things he or she is interested in, right? So the first and most important condition for it to be successful and our search to be effective is common language. Because without common language, there is no communication at all. So that's the condition, that's the solution. Not gonna happen, unfortunately, so we need to think about some alternative. There we go. We need to force user to formulate their query in a way that is easily translated to computer language. So we can go with the easy option. We can go with a filters type of interface when user has all those checkboxes, radio buttons, selects, and simply, clicks their way through the query. With the text search, though, it won't pass an exam because text search is basically rooted in a natural language, and as such, we get ambiguous and not exhaustive queries from a user. We have a collection of, texts, which are basically not well structured. And finally, and this is the main problem, I think, the relevance in a text search is not a Boolean value. It's more like a spectrum. Because with the traditional database queries, you have like either element is meeting given criteria or it's not. And if the criteria, if the criteria are met, then we have a relevant result, right? With the text search, it's more like, well, this text matches fully, this text matches, well, more or less, and this one is totally not relevant. So a spectrum, right? So do we have a problem? Yes, we have. But we have also information retrieval. It will be like Superman coming to the rescue. So what is it? So information retrieval deals with, I will say you only that the definition is somewhat descriptive. So the information retrieval deals with the representation, storage, organization of, and access to information items, such as document, web pages, online catalogs, structured and semi-structured records, multimedia objects. So full spectrum of elements, right? And the primary goal of an IR system is to retrieve all the documents that are relevant to a user query while retrieving as few non-relevant documents as possible. So, how does it really work? Imagine we have items. It can be collection of our, I don't know, products in our online shop, or it can be collection of texts, or it can be collection of music pieces, whatever. We prepare text representation, which we will call document, and the document in form of a text is nothing but a bag of word. And on the other end, we've got user with their information need that is somehow represented with the user's query. We can suspect that somewhere in the universe there is this ideal item that our user wants, and this ideal item, or actually collection of items, fits user needs in 100%. If we know this item, we can compare it to our collection and pick the most similar one. Or, more likely, we can prepare this ideal item representation and compare it with our collection. Unfortunately, we have no idea if such item exists, and if so, we have no access to that, right? So what we do? We have to make a bold assumption that the query user enters in our text field is some form of this ideal item representation. And now we can compare and calculate similarity between each document in our collection and the query with some kind of a ranking function, and we should get somehow relevant results. So, the relevance, because it's important and it's a keyword here. The relevance tells us how well a document satisfies users' information need, so how our documents are similar to users' query. And that's the base thing for information retrieval. So we have to have a collection to have something to work on. And our collection will consist from quotes, let's say from a text of culture, which were translated or encrypted by me, but in a quasi-language of my invention, so don't read it. I mean, when the text appears, you are not to read it, you just take a look at it. All important things will be highlighted somehow. It will help us to prevent from making assumptions, because when your brain sees the text, you automatically take some meaning out of it. And then you have your own ideas how the ranking should look like and how this text relates to the query. We don't want that. We want to focus on the mechanism itself, so no assumptions. And last but not least, you will have this unique opportunity to feel like your computer when you ask a question, right? Like a search engine. So let's start. Those are our texts. As you can see, No point in reading that. That's all about sweets, cupcakes, caramels, and this kind of stuff. I got very hungry each time I was sitting down to the presentation. So this is what our user wants to find. It's an actual query, also encrypted, right? So we get marshmallow, donut, caramel, and let's start. We don't want to read each text each time we change our mind about the way our ranking function should look like. So we are clever. We will build inverted index in a simplified version. Now it's Harry Potter magic. And we have our index, or rather part of the index. As you can see, the most important are those three terms from the user's query. And this index consists basically of two parts. There is the dictionary, and the dictionary are simply all terms from our documents collection, all unique terms, and they are, well, listed. And each term has its own postings assigned, and postings its hash-like structure, which contains reference to the document and the number of occurrences of a given term. Simple structure, easy to read, and very fast. So now let's get to measuring similarity. And okay, I admit measuring similarity between two texts seems a bit abstract, right? Because there is no easy way we can think of how to do it. And the wise people of information retrieval field came with the solution. Let's represent text as bit vector in a multidimensional space, each dimension corresponding with one term we are interested in, and the relevance will be simply similarity between those two vectors. In practice, it's something like that. We've got three important terms. We've got information retrieval and fun, and here is our table. So we've got two texts. The first, information retrieval, is fun, haha. And the second, we are having fun with retrieval, whatever that means. I just needed an example. So on the first dimension, the first text will have a coordinate valued as 1 because the information term is present in it. In the second text, it will be 0 because there is no such term. And we do that with every term we are interested in, and then is text vectorized somehow. Now we get to similarity, cosine similarity to be specific. Here is wise formula, how to do it. So we simply use dot product for vectors. So we take first coordinate of first vector, we multiply it by first coordinate of the second vector, then we do the same with the second coordinate and third coordinate, and until our coordinates are finished, and then we add it up together, and ta-da, we've got similarity. So first, let's prepare some kind of a matrix, and we have our three terms from user query, and the query obviously will have all ones in a table because each term appears in a query, and then documents will vary depending on the term is or is not within the document. And then we do our math, and the similarity gets revealed. So we have like 5 best matches, right? Let's take a look at it. And we can see that each of those best matches actually contains each term we are interested in. And some of them are appearing even twice or more times, right? So perhaps term frequency is something we should include in our calculation. Maybe the more times term appears, the better. It's true, but not all the words were created equal, because we are dealing with a natural language, and it's full of those pronouns, articles, prepositions, and this kind of words that actually bear no meaning or very little meaning. So we don't want to, compare two texts and say that they are similar simply because of appears in both of them. So we need to get what they are called stop words. So we are getting rid of the stop word from our user's query. And now our matrix looks like that, and the similarity changes. As you can see, two documents just drastically drop down in ranking. So let's take a look at them. Actually, no matches. But if we will take a closer look, we will see that one of them maybe doesn't contain caramel per se, but has something very similar. And if we see through our inverted index, we will see that there is also word caramelize and word marshmallowed. And we can suspect that our user may be interested in documents containing also these words, right? Because obviously there is some kind of semantic connection. So we have to get into the family business, and we have to find those related words, because in the language, as you know, there are those words families, and we have a base word like ideal, and then we have its family which contains idealistic, ideally, or we have a base word program, and there is this word programming, programmer, and so on, right? So we want to simplify our index and our query and work only on those base words because they are very similar to each other. And there are two tools to achieve that goal. We have something that is called lemmatization, and it requires some previous semantic knowledge and knowledge about morphological analysis. And basically, yeah, we're extracting the base word because we know about the processes that were in the language. And there is other tool called stemming, which is more like tactical and brute force. We simply remove words ending, and we hope that we got the base word. Of course, those tools will be different for different language, but we can find them online, and it's okay to use them. So when we adjust our metrics, and we will focus not on the marshmallow and caramel word itself, but the whole family of marshmallow and caramel, we will get a slightly different outcome, and now we can 7 best matches, which is not cool. So let's get back to the frequency. Let's think about query. If we have this query, Ruby programming, and we have texts, and each of those texts contain the word programming, and in some of those texts there is like Ruby mentioned, I don't know, 3 or 4 times, and some of them mention Ruby 300 or 400 times, we obviously can say that the last group is probably about Ruby, and therefore is relevant for our query. On the other hand, if we take this last group, in this group it doesn't matter if the word Ruby appeared 200 times or 300 times. The most important fact is that it is about Ruby, hence it's relevant. So we would expect that the scores with scores by similarity in the last group will not differ very much. And yeah, so we can say that the more frequent term within one document, the more relevant it gets, but up to a point, because above some point, each occurrence is not really meaningful and important. So wise people of information retrieval came up with this nice formula. Don't focus on it too much because it's one of many possibilities. I'm just putting it here so that you can be sure that I somehow calculated all the stuff in the tables. And there is another aspect of term frequency, which is called document frequency. Again, Ruby programming, again, texts about programming in each of the texts, and programming in C, so no Ruby there. Programming in various languages, so mentions about Ruby are. And the last group, programming in Ruby, plenty of Ruby. So, because programming is appearing in each text, we can say that it has high document frequency, because it appears in many documents. On the other hand, Ruby appears in a very few texts, so we have a low document frequency of the term, right? And it's a bit strange, yeah, but the less documents contain the term, the more discriminative power it has, right? So if only one text contains one term, this term is very specific for a given document. So we want to reward somehow the terms and the documents that are not very common. And this is done by inverse document frequency, IDE for short. And again, wise people of information retrieval came with this nice formula, and we take into account total number of documents in the collection and the total number of documents containing given query term. And we need to combine those formulas to get, as you can see, TF-IDF. TF-IDF is a weight or a measure that can be applied to number of to count of terms in a document. And let's do it. Let's do it because we want term frequency to be somehow involved in our calculation of similarity. As you can see, the results first got a bit lower, and second, we now see that it actually is a spectrum, and some documents are more fitting to the query than the other. So let's take a look at the winning 4. And yes, still we have matches by query terms. We can also see that the first document, which got the highest score, is the longest one. So perhaps it's because size matters. Perhaps the longer document, the more probable that any term appears. That would statistics suggest, right? So we need to somehow compensate it, because we can have in our collection short documents, long documents, and we cannot just, you know, cut number of words to some arbitrary chosen one. So longer documents should be somehow penalized because they have more words, so the bigger chance of hitting the term from the query. And the shorter documents should be boosted up because they have less words and a lesser chance of matching the query. And so, again, thank you, wise people of information retrieval. We've got something which is called pivot length normalization factor. And it takes into account average document length, which is our pivot, that is the value above which length of documents should be a bit penalized, and below which documents should be boosted up. And we have a slope. Slope can be adjusted, it depends on the collection. Elasticsearch uses Lucene underneath, never mind that. In Elasticsearch it's a 0.16, and we will stick to that number. And it's a normalizer, so we divide our TF-IDF similarity by this factor, and we should get the final score. So, before we get to the table with the results, I want to tell you that we just worked out ranking function of what is called vector retrieval model, or one of its variation. And our final formula looks like that. Say hello to the monster. yeah, don't focus on it too much, because, as I said, there are some other options, because each of element can be counted a bit differently. But what we have here, we have a numerator with a TF measure, we have denominator with our length normalizer, and then at the end we have our IDF measure. Yeah. So let's apply it. As you can see, in the top row there is length given, and if you compare TF-IDF similarity with our new normalized similarity, it actually becomes quite obvious that shorter documents got a bit of a boost, and longer documents got a bit of boost down? Not sure. Anyway, we can ask, is that all we can do? Can we do anything better? Yes, we can. We can use, for example, synonyms. And as it happens in our language, in my language, marshmallow has two synonym words, chupa chup and wafer. And if we check with our inverted index, we have two documents containing those synonyms. And now we have to do something which is called query expansion, because our user asked us about marshmallow caramel. We know that marshmallow has synonym chupa chup and a synonym wafer, so we just assume that our user might have asked us about marshmallow, chupa chup, wafer, caramel. And we count similarity for those words. As you can see, document 9 and document 11, which contained synonyms, actually were quite boosted, and they are right now at the top of our ranking, because our ranking right now looks like that. And we have 11 documents neatly sorted, ranges that goes with the color are somewhat arbitrary picked. I just looked at it, and it, well, looked nice to divide it this way, because they are clustering together. So we have, and the important thing is that those ranges you need to adjust, because it depends on the collection. So you have to do it through the experience, actually. And you have to learn your documents and learn your data. Okay, so we have two top documents. We have 6 more or less matching documents and 3 documents that are rather not relevant. Can we do better? Yes, we can. We can boost our documents if exact user query appears in it. We can boost our documents when they contain all query terms, because, as you may suspect, our ranking also includes documents where only, I don't know, 50% of terms appeared. We can boost documents with the similar ordering of terms as it is in query. We can prepare wider search, because user might have misspelled the word, and users are known to misspell the words. We have plenty of other options, and if you go deeper into information text retrieval, information retrieval, yes, and text search area, you will discover each and every one of them. But we won't do that, because we have like 11 minutes left, and it would take a moment to count all the stuff. So we want to sum up somehow things about text search and information retrieval as such. So first and foremost, relevance is a spectrum. Second thing is that relevance can be viewed as similarity between query user entered and the document in our collection. And we can count it with vector magic. And the count of terms is quite complicated area and asks for TF-IDF measure. And length normalization generally pays off because our documents for sure will differ in length. And last but not least, semantics cannot be avoided, but we can control it to some extent with the use of stop words, with the use of synonyms lists and related words finding. And yeah, we can, I don't know, prepare controlled vocabularies, and there is plenty of possibility here. Important note, vector model, which we discussed, is one of many models, and it goes really well with long texts and not that structured. As for more records like or database-like structures, it is better to use another model, which is called BM25F, which is probability derived. And yeah, that's the important note. And now the moment that we will learn what our user was actually searching for online. Well, that was meaning of life. And sorry, I have to tell you that I had no idea how results will shape at the end. It was just experiment while I was preparing this talk. And quotes were selected a bit randomly from Goodreads, not all of them. And the best match, here we have Anthony de Mello. You may want to read it, but I'm not sure, because, yeah, don't blame me for the quotes. There is another, somewhat shorter, and those are our winners, right? And not really matching. I so regret Henry Miller didn't make to the final. Yeah, to the final. Another list of somehow matching. And finally, what was rejected. So our retrieval system decided that definition of life for Diablo is not really relevant for meaning of life, as well as this guy thought. And Monty Python text about fruit fight is also not relevant. I disagree personally, but what can you do? It is what it is. Yeah. And that's it. I mean, okay, one suggestion. If you are looking for the meaning of life, I truly encourage you to go and watch Monty Python's Meaning of Life movie, really. And at the end, there is a scene where the meaning of life is revealed. Yes, I recommend that. And that's one thing. And the second thing is that digest it, think about it, and if you happen to have any question regarding my presentation, I will be really glad to try and answer it. Because I cannot make any promise, because it's a really huge area, and yeah. So find me later and ask me this question, and I will go like thinking, and now that for now it's all. I don't know what now. Thank you. Thank you.